Would anyone like me to go over their homework from yesterday? Alright, phones away, guys. Grab your workout. Is there anything there anyone would like me to go over? Dennis, would you like this back? Based on the stuff that we did. Back pages. I got one of Lewis diagrams on 4 diagrams. Okay. Luca. Okay. You never handed yours in. That's well, then you. I think you're going to get more time to do it anyway. Michael, would you like this back? She did, but then we went over what Lewis diagrams look like. I spent a bunch of time yesterday. You guys are up on the board redoing the Lewis diagram stuff. These aren't Lewis diagrams. These are 4 diagrams. This one, it says ionic bond. Show the sequence of Lewis diagrams. Lewis diagrams. 4 was just the first section. So the more diagrams are there. Lewis diagrams. I want you to draw me the transfer. So these magnesium, is that magnesium? There's magnesium, there should be 2 chlorines. Yeah, so you give me this. They shouldn't be overlapping because they're out. It should be the transfer of one to the other. So you know even that guy needs some tweaking. Michael, would you like this thing back? Elijah, would you like yours back? These are correct. Currency. You like the back page looks so we went yesterday we went over what Lewis diagrams should have gone over with the TOCs. So then a bunch of you said these were probably wrong for Monday. So a bunch of you wanted it back to go back and fix the misunderstandings with the Lewis diagrams. That's why I'm offering them the handback. If you'd like to go back and take a look at it, based on the stuff that we did yesterday, you can. You don't have to take it back. You can. You can leave it as it was. All right. Sorry? You have done it.
You can. Mr. Rudolph has seen me.
Okay, Carly, you want yours back or are you happy with it? Yes, you want it back. Tavares, you want it back or are you happy with it? Vikram.
Oh.
Good. Lexi is doing leadership things. Number, you want yours back or are you happy with it?
I don't know.
Yes.
Yeah.
Take it back.
Does it like tell you it's wrong?
No, I haven't marked it yet. You have to figure it out based on stuff that we did yesterday. You are welcome. Memphis. Cool. This as well. Lab in, love it. Quick, let's go. Okay. Oh, now why am I sitting down? There's one more thing I want to give you guys. Some of you have grabbed this already. Some of you still need to. The stuff that we are going to be doing today is it's useful to have a larger periodic table. So I have a whole bunch of them. If you've taken one already, it probably wasn't a whole bunch. Every one of you needs to grab one of these big periodic tables.
Yeah,
don't know which one of you is Liam. Wow. Yeah, real quick.
You're missing one.
No, Liam got you. Liam got you.
Malik is here.
Thank you, Liam. She said baby.
Okay.
I said maybe. I did the maybe.
I can never get it.
Okay, here we go. So, yesterday we looked at simple ionic compounds, naming and formula writing. Today, we're going to look at the last two types of ionic compounds, the multivalents and the polyatomics. Both of which you would have looked at in grade 9, but we will review today. So, the multivalent metals, here we go. If you look at your periodic table, you will notice that in the positive ion section, or in the metal section, there are a whole bunch of elements there that have, in the section where you're looking for the ion charges up in that top right-hand corner, there's a whole bunch of them that have multiple charges listed there. Those are called valence numbers. And what they mean is, for example, something like manganese. Manganese is Mn, it's this guy right in the middle of the table, column 7. If you look there, manganese can be +2, +3, +4, +6, or +7. Based on the structure of that atom, it can give away different combinations of electrons, depending on what it feels like doing at any given moment and what it's reacting with. And each one of those different brands of manganese, every time it has a different charge, they have different properties. So you can't all treat them the same. And so there needed to be a way devised to make sure that we're keeping track of which charged element we're looking at, or which charged ion we're looking at, when we've got a single element with multiple possible charges. That's what we mean when we talk about these multivalent metals. So, there are some metals that have different valence numbers. Those are those ionic charges. There's different valence numbers listed there. This means they can form multiple different ions. And then the example that I just gave you is manganese. Manganese, when it ionizes, can form Mg+2, or Mg+3, Mg+4, Mg+6, or Mg+7. Those are all options for manganese. And the properties that they form are different. So we must treat them differently because they behave differently. Another example is copper. Copper is probably the most common one. Well, copper and iron are the most common ones you'll look at. Yes. Yes. Thank you. Mn, not Mg. That's magnesium. Thank you, Olive, and whoever else caught that but didn't say anything. Mn, 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 and Mn. Oh, I made that mistake in the last block and nobody caught it. Whoops. Okay. Copper's another one. Copper can be Cu+2 or it can be Cu+1. And so to distinguish between these, you guys would have learned last year that Roman numerals are used to separate out these different brands of manganese or copper or whatever other multivalent element you're looking at. The Roman numerals. Here's the review for the Roman numerals. It's interesting. Every time there's another Super Bowl, people start searching for the meanings of Roman numerals. We just had a Super Bowl. So, the Roman numerals should be fresh in everyone's mind. The Roman numeral for 1 is? Sorry? It's I. Sometimes it's given like the lines on top and bottom. Sometimes it's just a vertical line. The Roman numeral for 2 is 2 I's. The Roman numeral for 3 is 3 I's. The Roman numeral for 4 is IV. 1 less than V. Because V is 5. And 4 is 1 less than 5, so IV. 6 is VI, 1 more than 5. 7 is VII. And 8 is VIII. And that's all we need. There's nothing on the periodic table that has a valence number bigger than 8. So when we've got something with multiple charges, whatever the charge is, will tell us what Roman numeral to use. So if I have Cu plus 1, what's that thing going to be called? Cu is copper. Yeah, it's going to be copper I, and that I is going to show up inside a set of brackets. And the copper with a charge of 2 is going to be called copper in brackets II. Flip the page when you're ready. So, naming rules. It's almost the same as before. The metal comes first, or the positive ion, whatever it is. If that metal, the positive ion, has more than one charge, you include the Roman numeral. If it doesn't, you don't. So you only include a Roman numeral if whatever is there has multiple charges. And when we're naming, we have to figure out what charge we have if there's multiple ones listed on the table. So we'll go through that process. The nonmetal is given the suffix IDE, and it doesn't matter how many of each atom are in the compound. So let's do an example. I've got, if you look at these two examples, I've got Fe2O3 and I've got FeO. It's the same elements in each of those compounds. One's Fe is iron and O is oxygen. So in both of these, I've got iron and I've got oxygen. Oxygen becomes oxide. And I've got iron and I've got oxide in both of these examples. But if you look at the periodic table, iron is one of these guys right here that can either be +3 or it can be +2. So we have to figure out which is which. Because multiple charges exist for iron, we're going to throw the brackets there in the middle. And now we have to go ahead and figure out what the charge is on the iron so we can put in the correct Roman numeral. There's two ways to do it. They're related to the two we looked at yesterday, either the swapping and dropping or the longer mathematical method. I'll show you both. So we've got Fe2O3. We know the charge on oxygen. The charge on oxygen is always what? -2. So the kind of longer mathematical way to do this is to say, okay, well, If I have 3 negative 2s, what's the total amount of negative charge coming? Negative 6. Which means my ions have to bring how much? Sorry? Positive 6. The total amount of iron has to balance out the total amount of oxygen. If I've got 3 negative 2s, that's negative 6, and the total charge for my iron needs to be the same. Because when these ionic compounds form, they balance out the positive and negative charges. So, we're told in the formula that I have 2 irons. What does the charge on iron have to be if 2 of them give me 6? 3. 6 divided by 2 is 3. So then the charge on the iron up here needs to be plus 3. So we're going to go back to the name, put the Roman numeral inside, and we're done. Another way to look at the same thing is to do this. Okay, if I'm going to use the swapping and dropping method, I've got Fe2O3, and I'm going to swap and raise them. That's going to be a 3, that's going to be a 2. Now all you have to do is check, is this the right charge on oxygen? Is oxygen charged 2? It's negative, but yeah, it's 2. So if this number is right, then this number must also be right. So iron's going to have a charge of 3. 2 ways to look at it. So then FeO, let's do the same thing. If I have FeO, if there are no numbers listed, sorry Dennis, you good? Okay. If there's no numbers listed, there's one of each. Good. So I'm going to force those ones in there. So it's 2, because I've got the charge on oxygen is 2, that's going to be minus 2, so the iron's going to be plus 2. And if I've got 1 iron bringing me a charge of plus 2, someone said it already, that guy's going to have to be plus 2. If you do choose to cross with something, you have to do the opposite of reducing. I'll show you what that looks like in a second. So we've seen it already. We're plus 2 here. So Roman numeral 2 goes in there. If you're going to use swapping and raising, that's going to go up and that's going to go up. It's going to be a 1 and a 1. You have to check, is this the right charge on oxygen? Is oxygen charged 1? No, it's charged 2. So to take 1 and turn it into 2, I have to multiply this thing by 2. And whatever I do to one, I have to do to the other. Luke and Dennis, you guys okay? Am I losing you? Have I left you behind somewhere? Both of you look distressed. Would you like me to slow down? Okay. Are there any questions about what I've just done? Okay. We're going all the way to page 77. Because this is review number F. If you remember it from last year, go ahead. Okay. I want you guys, look, I'll leave what's on the screen. I want you to take a look at these bottom 4. I want you to try what I just reviewed. Lead with a Roman numeral of 4 fluoride. You're going to get tin with a Roman numeral of 4 phosphide. You're going to get iron with a Roman numeral of 2 iodide. And you're going to get nickel with a Roman numeral of 3 sulfide. Comments, questions, concerns? Would anyone like me to go over any of those 4? Going once. Going twice. Thrice sold. Okay, cool. Flip the page. The formula writing is easy. The formula writing is the same as before. And we don't need to worry about which charge we're using because it's in the name. So the formulas of ionic compounds with multivalent metals is the same as before, what we did yesterday, but use the ion charge given by the Roman numeral. Roman numeral. It's that blank there. That's it. So I'll do one example, and then I want you to do the other 5. I'll do iron 2 phosphide. Okay, well, iron is Fe. If I'm going from the name to the formula, iron's Fe, you find it on the table. That Roman numeral 2 tells us that this is the charge we're supposed to use for the iron. The iron is +2. Phosphorus is P with a charge of -3. And now we can just swap and drop. It's going to be F3P2, Fe3 rather, P2. And then we reduce if we can. We can't because it's 3 and 2. We can't divide 3 and 2 by the same thing. So we're done. Swap, drop, and reduce. If you can divide something out, you must. Okay, take a look at those other 5. The procedure is the same. If you need a hand, let me know. Okay. Okay. Okay, how are we doing with these 5?
Charge given by the government. Because sulfur is a thing, we saw with pH 4 and F. Depends on if you're American or British. You'll see it both ways. And some periodic tables have with the F a lot with the pH. We're going to in a second, yes. Okay. Okay, here are the answers to these 5 that you should have done. Let me know if you have any comments, questions, concerns. Would anyone like me to explain any of them? There is one tricky one there. Bottom left. The bottom left was the one I tried to use to trick you. If you swapped and dropped, then you also got to reduce. Questions, comments, concerns on any of those? Which one are you looking at?
The last one.
The last one, that's RE2S7. Okay, if there are no questions, then let us look at the last concept today. This, ladies and gentlemen, is a chart of what are called polyatomic ions. It is on there. So, there are ionic compounds. I think, Himparis, you asked about this yesterday. There are ionic compounds where you can have 3, 4, maybe 5 different elements in there. When you have more than 2 elements present in an ionic compound, you have to look at the polyatomic ion chart. Because somewhere in there, there is an ion that is built of multiple elements. And those things come together and then they behave as a single ionic particle. This on the notes is a list. This is not an extensive list. There are more, which is why on this gigantic table, I have a list on the front. So some common polyatomic ions. This list is not the same. It's similar. And if you look, some of the names are different. If I look at this guy right here, I've got hydrogen phosphate, which is HPO4, charge -2. But if you look down here, HPO4 with a charge of -2 is also called monohydrogen phosphate. Same formula, 2 different names. If you look at the back of your giant periodic table, flip it over. There's another chart. And about halfway down, you're going to see some bigger, there's 4 of them that look larger. There's supposed to be a comma. There, 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 and there. So hydrogen, so HCO3 with a charge of -1 can be called either hydrogen carbonate or it can be called bicarbonate. Hydrogen sulfate can be called hydrogen sulfate or bisulfate. HS can be hydrogen sulfide or bisulfide.
HSO3 can be hydrogen sulfite or bisulfite. You can use either name, you don't have to use both. For example, HCO3, hydrogen carbonate, is a polyatomic ion. Almost certainly, I would bet large sums of money you could find it in your kitchen or your pantry. Because if you take sodium and you put it together with hydrogen carbonate, you get something called sodium hydrogen carbonate, or also called sodium bicarbonate, common name, baking soda. In the kitchen, we call it baking soda. In the chemical or in the chemistry lab, we call it sodium bicarbonate. They are the same thing. You could also call it sodium hydrogen carbonate. Same thing. So let's take a look at how these guys behave. There we go. The naming and formula writing rules for polyatomic ions, again, are similar to before with one extra little snag. So the naming. If you see more than 2 types of elements listed in a formula, you got to look for a polyatomic ion chart. Sorry, you have to look for a polyatomic ion from the chart. This big one here is the one that I will give you on any test quiz you write for me. So nothing, if it's not found on this page on one of these 2 sides, you're not going to have to use it. So, for example, if I throw this guy down, MgO, there's only 2 elements listed, magnesium and oxygen. Magnesium only has 1 charge. Because there's only 2 listed here, there's no polyatomics. No polyatomic ion. This thing would just be magnesium, no Roman numeral because it's only got 1 charge, oxide. But I might give you something that looks like this. MgC2O4. How many elements are there? 3. As soon as you see more than 2, pull out your polyatomic ion chart. So we have to either find, it'll take some practice getting used to what combination of elements you're supposed to be looking for. It's either going to be MgC2 or it's going to be the C2O4. One chunk of this is going to be a polyatomic ion. We have to go find it. Yes. Depends on how the charge is balanced. I'll show you in a sec. If there's multiple of the ion, then the ion needs to be in brackets. But if you only have 1 of them, it doesn't have to be in brackets. Okay, so see if you can find it. Look at your polyatomic ion chart. Which piece is the polyatomic ion? I'll give you a hint, it's not on the back. Save some time, it's on the front. Yes. Number found it already. See if the rest of you can find it. I'll give you another hint, it's on the far right-hand side. It's oxalate. Lots of you are finding it. This piece right here is a polyatomic ion. So now that we've found it, we just use the name as it's written. This piece here is going to be oxalate. Oxalate. The Mg is magnesium. There's no multiple charges there. So this is just going to be magnesium oxalate. Done. All the other naming rules apply. If this thing had multiple charges, we need to throw in a Roman numeral, which I will demonstrate at the bottom. Okay, formula writing. If the name, or the word the should be there. If the name is not on the periodic table, check the polyatomic ion chart. If you're struggling to find it, if the chemical name has 8 or ite, at the end, it's definitely a polyatomic ion. Because if it comes off the periodic table, it ends in IDE. So if it ends in ate or ite, it's polyatomic. If the second name listed does not end in IDE, it's definitely polyatomic. And if there are more than 2 elements in the name, check the chart. Okay, I got 6 examples here. Let's do them all. I'm going to change one of them. So if you rushed ahead and did it, you're going to have to change one. First one, I've got NH4 in brackets 3 with a P. Big clue. If you see something in brackets, it's a polyatomic ion every time. So let's go find NH4. What is NH4? Someone said it already. It's ammonium. We use the name as it's given. So then what's P? It's phosphorus. And when we name it, we change the end to ide. So it's going to be phosphide. Sorry? I have not said which one I changed. Bottom left. I will in a second. Okay, next one. Al and then in brackets OH3. The brackets tell you if there are brackets, that's definitely the polyatomic ion. So what's OH? It's hydroxide. So let's throw that name down. And then Al is aluminum. Does aluminum have multiple charges? It does not. So there's no Roman numerals. It's just aluminum hydroxide. This one. This is the one I want to change. Here's what we're going to change it to. Instead of K2Cr2O7, we're going to change this guy to Cu2Cr2O7. Cu2Cr2O7. Okay, no brackets in this one, but there's definitely 3 elements there. So because there's 3 elements there and it's an ionic compound, you have to go look at the polyatomic ion chart. What is the polyatomic ion there? Sorry? It's dichromate. Good. This piece right here, the Cr2O7, is the polyatomic ion. So we can start putting the name together. That guy is dichromate. And then the Cu is copper. What's the snag with copper? It has multiple possible charges. So now we have to throw the brackets in there and we have to figure out what the Roman numeral for copper is going to be. You're right. Let's prove it. Actually, you're wrong. Let's not prove it. Let's show why. You said it was 2? Not 2. Okay, so I've got Cu2 and I've got Cr2O7. Now the Cr2O7, because there's no brackets around it, that just means I have one of the thing. What's the charge on Cr2O7? -2. So if I have one Cr2O7 bringing -2, then the copper's got to bring +2 to balance it out. I have 2 coppers. So if I have 2 coppers and their total charge is +2, then each copper needs to have a charge of what? It's got to have a charge of +1. So then this is going to give us a Roman numeral. So then that thing would be copper, Roman numeral 1, dichromate. Cool. Almost done. Last three. So that was formulas to names. Let's go names to formulas. I got lithium hydroxide. So hydroxide, it's not obvious every time that hydroxide is a polyatomic ion. Lithium's definitely not. Hydroxide is, but why? If you take a look at that name hydroxide, it sounds a little bit like hydrogen, sounds a little bit like oxygen. There's two elements within that name, which means I've got three elements total, which means one of them has to be a polyatomic. Lithium's just Li with a charge of +1. Yes, hydroxide is in fact OH. And now what's the charge on OH? It's -1. So if lithium's +1 and OH is -1, I just need one of each. It's going to be LiOH. Another common one is potassium permanganate. Potassium is K, +1, you betcha. Permanganate, that name sounds weird. The name sounds weird, it's probably in the polyatomic ion chart. Also, it ends in ATE, so it's definitely in the polyatomics. Yeah, it's in that middle column if you haven't found it yet. Some people have started to already. Permanganate is MnO4, it's got a charge of -1. So then potassium permanganate is just going to be KMnO4. It's a really pretty chemical. It's purple. When it burns, it gives you this lovely purple smoke. Also happens to be pretty toxic. But at least when you're dying of toxicity, it's pretty. It's got to be some upside, right? Okay, last one. Iron Roman numeral 3 hydrogen sulfide. 3 names. There's a polyatomic in there. The polyatomic is going to be this piece here. It is not FeHS. Well, let's take a look. Iron with the Roman numeral 3 means what? It has a charge of 3. So iron's going to be Fe with a charge of +3. And now you got to go find hydrogen sulfide. I'll give you a hint. It's on the back. It's not on the front. This one's on the back. For the sake of time, I'll tell you where to find it. Take a look at the back. Put your phone away, Yar. No one should be on their phones right now. Hydrogen sulfide is what? It's HS. What's the charge on it? -1. So now, if we're going to swap and drop here, I'm going to need 1 iron, so that's just going to be Fe, but I'm going to need 3 of this whole ion. So if you need multiple of an entire polyatomic, you have to take that polyatomic, put it in brackets, and then put the number that you need on the outside of those brackets. So we've got Fe and then in brackets HS bracket 3. That is iron Roman numeral 3 hydrogen sulfide. Comments, questions, concerns on what I've just done? Sorry? Class ends at 10:44. So, here is what I'm assigning unto y'all for practice for the rest of class in the 4-day weekend. All of page 77 is too much. So, I'm going to assign just question 1 and just question 2 on page 77. And I'm going to assign aces. Aces means every other letter. A but not B, C but not D, E but not F, G but not H, etc. Every other one. You may need to show more work than the space allows for. Use the whiteboards. Use some scrap paper. Don't cram everything in if you need to. Use more space. Bell goes at 10:44, which is 16 minutes. But I think it was going 2 minutes earlier. So you probably got 14 minutes. Everything we've done yesterday and today is mixed in here. You've got multivalence, you've got regular ionics, you've got polyatomics all mixed together. All the rules we've done over the last 2 days are in here. On your market set, go. This is what you're working on for today, and we'll go over it on Monday. I will have more practice, Tuesday. I have more practice, which we'll spend some more time with next week. Gives you lots of practice naming and formula writing. On your market set, go.